we are going to discuss about the second property of colligative properties. As we discussed earlier, we should know what is a colligative property. I just want to remind you what is a colligative property. Colligative property are the properties of solutions. They are the properties of solutions. And these properties depend upon the number of moles of solute particles present in a solution and not on their chemical nature on any account. That is the importance of this property. They never depend upon the chemical nature of the solute particles. So we have four colligative properties. The first one is relative lowering of vapor pressure. Second one is elevation of boiling point. Third one is depression of freezing point, and the last one is osmotic pressure. Already we have seen about relative lowering of vapor pressure, and now we are going to see about elevation of boiling point. Before going into it, we should know what is boiling point. Do you all know what is boiling point? Yes. Boiling point is the temperature at which a solution boils. When does a solution boil? A solution or a solvent boils, or a liquid, we can generally say it as a liquid. A liquid boils at a temperature at which the vapor pressure of that liquid becomes equal to the atmospheric pressure, that is 1 atm. At that temperature, the liquid begins to boil and we call it as boiling point. Okay. Now, in this colligative property, we are going to compare these properties of a pure solvent and that of a solution. Solution, that is by dissolving a solute, non-volatile solute into it, and we will observe what happens to that property. That is what we used to do in this chapter. See, in elevation of boiling point, first let us take a simple known solvent. We all know water is a very good solvent, and I believe you all know the boiling point of water. What is the boiling point of water? Yes, it is 100 degrees Celsius. See, it can be the elevation of boiling point is described in this graph. We can understand by observing this graph. See, in the x-axis denotes the temperature and the y-axis denotes the pressure of the atmosphere. And the first curve, the first curve represents the pure solvent. See, as we increase the temperature of the pure solvent, the vapor pressure of this solvent increases, and at this particular point, the vapor pressure of the solvent and atmosphere becomes equal. That is 1 atmospheric pressure. See, note the temperature 100 degrees centigrade. So, only at 100 degrees centigrade, the vapor pressure of the water, that is pure solvent. This graph actually, it is for water only. So, for water at 100 degrees centigrade, the vapor pressure is equal to the atmospheric pressure, and hence water boils at 100 degrees centigrade. Now, what we are doing is, we are going to dissolve a non-volatile solute into water. So, after dissolving it, let us boil it. Let us increase the temperature, or let us heat it. So, as the temperature increases for this dilute solution, the vapor pressure also increases as we heat it. See, at this particular point only, the vapor pressure of the solution becomes equal to the atmospheric pressure. So, it is not at 100 degrees centigrade, but at a temperature higher than 100 degrees Celsius. So, what we can conclude is, when we dissolve a known amount of solute in a solvent, the temperature, the boiling temperature of that solution increases. Can you say the reason for this? Yes, actually we have discussed already in the relative lowering of vapor pressure topic. When you dissolve a solute in the solvent, what happens is, and when you heat it, the vapor pressure is less. So in order to make it equal to atmospheric pressure, we have to heat the solution more. So what happens? The boiling point naturally increases. Only at a higher temperature, the vapor pressure of the solution becomes equal to the vapor pressure, atmospheric pressure, and hence the solution boils at a higher temperature. See, this can be used in determining the molecular weight of an unknown solute. It is the importance of this topic. For that, we have to derive an equation. Here, see, we can clearly understand that. Let us consider like this. Boiling temperature, boiling point of, or boiling temperature of a pure solvent. Let it be T. Since it is a temperature, boiling temperature, we can denote it as boiling temperature also. Since it's a temperature, T. Since it's boiling temperature, B. And we always give a naught for pure solvent. So, TB naught. Now, boiling point of, or we shall say it as temperature. It would be more suitable. Here also we can take it as temperature, denote it as temperature. Boiling temperature of a dilute solution or a solution is the same temperature, same boiling temperature, but we need not denote it as, we need not give this not to it. Let us simply denote this as solution. As we discussed, as I told you earlier, the boiling temperature of pure solvent is lesser than that of the solution, or in other words, the boiling temperature of the solution is greater than the boiling temperature of the pure solvent. So, the difference of these two temperatures, let us denote it as delta. And since it's a temperature T, and since it is a boiling temperature TB. So, what is the delta TB denotes? It is the difference between the boiling temperature of a solution and the pure solvent. So, this is given by, see, this is higher one. So, TB minus T naught B. So, this gives the difference in boiling points of the pure solution and the pure solvent. See, according to Raoult's law, Raoult comes here, and according to Raoult's law, this delta TB, that is the elevation of boiling point, we can simply call it as elevation of boiling point. This is directly proportional to molarity of the solution. It is directly proportional to molarity of the solution. See, molarity, L-I-T-Y and not R-I-T-Y, molarity of the solution. So, in equations, we used to take this proportionality and put this equal to. So, when you make it as is equal to, we always introduce a constant, and that constant is K. Since it is here, it is boiling, we are dealing with boiling point. The constant can be denoted as KB into M, where delta TB represents the elevation in boiling point and KB is molal elevation constant, or it is even called as ebullioscopic constant. KB is molal elevation constant, or it may be stated as ebullioscopic constant. Ebullioscopic constant And as I told you, M denotes the molality of the solution. Now what we have to do is, we have to substitute the expression for molality. So we should we should bring out the expression for molality. I think you all know what is molality. It is actually a concentration term of a solution. We have many concentration terms such as molality, molarity, normality, formality, and so on. Is it not? Like, what is molality? Molality is the number of moles of solute. It is the number of moles of solute in a solution by weight of solvent in kilogram. You have to express the weight of solvent in kilogram. And you can easily say the expression for number of moles of solute. Is it not? What is number of moles of solute? Number of moles of solute is the mass of the solute by the molar mass of the solute. See, we can put this equal to here. And by weight of solvent in kilogram. Solvent is denoted by the letter A. So, WA. Since it has to be expressed in kilogram, it should be divided by 1000. So, this equation becomes like this: WB by MB into 1000. When it comes here, we have to write the reciprocal of it. 1000 comes up and by WA. See, this is the expression for molality of that solution. Now, we have to substitute this expression instead of M in this equation. So, this equation becomes delta TB is equal to KB into, write this expression instead of M. So, into WB by MB into 1000 by WA. See, you have to know the terms in this equation. Then only you can substitute the values given in the problem. See, delta, once again I am telling you, delta TB is the elevation in boiling point, KB is the molar elevation constant or ebullioscopic constant, WB, B always denotes solute. So, weight of the solute or mass of the solute, this is the molecular mass of the or molar mass of the solute, and WA is the mass of the solvent. So, from this equation, how does this equation help us? This equation helps us to calculate the molecular weight of the solute. See, so this equation can be written as MB and this delta DB goes here. So, what happens? KB by delta TB into WB by, bring this WA here. So, the equation looks nice, into 1000. So, this is the equation for calculating the molar mass of a solute. And this equation can also be written like this: M2 is equal to KB by delta TB into W2 by W1 into 1000. Whatever it is, we should understand B or 2 denotes solute and A or 1 denotes solvent. Thus, by using this equation, we can calculate the molar mass of an unknown solute using this equation.